What does Varimax do? It's a type of orthogonal rotation. What does orthogonal mean? Uncorrelated factors. Right? It literally takes the vertices and just rotates them, just like this. It keeps them orthogonal, which means it results in uncorrelated factors or components. Varimax cleans up the factors. It cleans up the columns. So Varimax focuses on the columns, makes them as interpretable as possible. The goal is to maximize the variance of factor loadings by making high loadings higher and low ones lower. So, if you look at this, everybody, just for this extreme example, pretty interpretable, isn't it? In fact, that's why sometimes they compare them to what's called simple structure. Simple structure means that, you know what? High loadings, low ones. High ones, low ones. High ones, low ones. So this is Varimax, everybody. So, what if you decide that you want to examine sorted factor loadings greater than 0.5? Let's just say you decide, you know what? I want my loadings to be accounting for at least 25% of the variance for that item. There are some kind of cool things you can do in SPSS called sort and blank 0.5. And for, how do you get that? By point and click, everybody? If you want to do that, you just go into under options, you can sort by size if you want to. Or you can suppress small coefficients. The value must be at least 0.5. I mean, there's different ways that will help you understand the output. For a small number of items, I don't see the necessity of doing that. If you have like 80 items, if you have a huge, right, inventory, this might be really helpful. So here, do you see what it did? It just suppressed any of the ones that were less than 0.5.
Makes it a lot easier to read.
Yes, it does. Yes, it does. But you can't calculate communalities from this, can you? Because or eigenvalues. Right. But it does help make it much interpretable. Which shows you that last factor, something's going on there, isn't it? So, Varimax cleans up the columns. Quartermax cleans up the rows. Another type of orthogonal solution cleans up the rows. Rotation is done so that each variable loads mainly on one factor. And it simplifies the variables by increasing the dispersion of loadings within variables. So in other words, however, there is some problems that may result in general factors with high to moderate loadings. But here you have, everybody, we're trying to clean up the factor, the item. That makes it pretty clear that goes with the first component, doesn't it? Yeah. And here again, you see the rotated component matrix using Quartermax. So sometimes what I do, everybody, is I do different types of rotations, just see if the solution is very different. Exercise, 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 and a couple of the diet ones seem to go there. And there's that lingering one there, right down there, the one item construct. Equimax, though it behaves a little erratically, is a combination of Varimax and Quartermax. Simultaneously cleans up the rows and the columns. The rows and the columns. Again, very similar solution. And sometimes it's nice to do different types of rotations just to see if they come to be equal or the same. But in the social sciences, is there a chance that things are related? Is there a chance that organization commitment and employee engagement are correlated? What about things such as risky behaviors and health? Could there be a correlation? Absolutely. Which means we turn to the second major camp of types of rotations called oblique. Oblique rotation means uncorrelated. Correlated. The oblique rotation lets the constructs, factors, components, dimensions correlate. The factor loadings are still basically types of partial regression coefficients, but since they correlate, they're no longer equal to the simple factor variable. In other words, it takes into account the correlation of the components, which probably mirrors psychology, doesn't it? It's very doubtful if I have a construct called organization commitment, one called job satisfaction, one called organizational stress, that they're going to have correlations of what? If I do orthogonal rotation, I'm imposing an inter-component correlation of what? If they're orthogonal, I'm imposing an inter-component correlation of what? 0. Right? We're assuming they're unrelated. So here, everybody, one of the options is called direct Oblique. That's the main one in SPSS. There's different types of oblique rotations in different softwares. One I sometimes use that's a combination of both is called Promax. But direct Oblique will be fine. You can leave it at the default of delta, which kind of weights the loadings.
So that's the one you suggest is direct Oblique?
Yeah, it's a direct Oblique. Basically, the delta sets the extent of obliqueness. Less oblique as d becomes negative. What does it mean? You can actually set how much of the relationship you want them to be. You see, the way to think about this even geometrically, everybody, to think about this geometrically, this is component 1, this is component 2. Does everybody see? Looking at the arc, 90 degrees, take the cosine of 90 degrees, and I guarantee you the cosine of 90 degrees equals 0. But now, what if I let them correlate? Right? Which means this kind of visually captures oblique rotation, because you're moving the vertice based on the default. Or you can actually set it, if you have some justification, the extent of intercorrelation you want to impose. Here you're going to find a lot of stuff is very similar. Same communalities, same variance explained, 3-factor solution. It looks exactly the same as our initial solution. So look, everybody, compared to Verimax, it's pretty much the same. Now what is slightly different? You get initial eigenvalues, extraction, sum of squared loadings, which is the same. But then, looking at rotation loadings, you get this 1.038. So that's the rotated one, which looks kind of similar to this, because it takes into account the extent of obliqueness. See, look at what it says. When components are correlated, sums of square loadings cannot be added to obtain a total variance, because there's interrelationship of the constructs. And here you get 2 types of rotated matrices. 2 types. And this will serve you well if you remember what you used to get in discriminant function analysis. Because you get a pattern matrix and a structure matrix. The pattern matrix is the relationship of the item and the variable holding constant the other variables. Which kind of is like the standardized coefficients you got in discriminant function analysis. So the pattern matrix is the relationship of the variable, and it's kind of like standardized coefficients. And if it's a covariance matrix, it's like unstandardized regression coefficients that are partialed out. So here again, you see the 3 items for exercise, you see the items there, and you see the big one there. So this is the pattern matrix, which often is used for interpretation. However, the pattern matrix is analogous to partial standardized coefficients. The importance of the item with other variables partialed out. Some opine that the meaning of the factors is ascertained from the pattern matrix. However, similar to that article I showed you by Bruce Thompson on discriminant function analysis, I would use both the pattern matrix and the structure matrix. The structure is the correlation. It's kind of like a 0-order correlation, not parsing out the other variables. So this is very similar to the structure matrix you got in good old discriminant function analysis. This is the relationship of the item with the component, not partially known. So my recommendation for oblique rotation, everybody, is to use both of these. And just see if they give a similar result. Hopefully they do. Hopefully they do. Do they sometimes differ? A little, but usually not a lot. If it's a clean solution, you have nice communalities, okay sample size, they're not going to see a huge difference. So here, everybody, what you do get now from oblique rotation is a correlation matrix of the constructs, or the components. You do get a correlation matrix. It's called component correlation. Because now with oblique, we're allowing them to correlate. So there you see the first one and the second one is 0.388. The others are really low. This will shed insight why a two-factor solution had a worse fit. Do you remember we kind of went down to 54%? Because look at these. Really low. Really low. So that's oblique. So now you know the different types of orthogonal rotations. The one we'll use for this class for oblique is the direct Oblimin. There is another option called Promax. It's an alternative, non-orthogonal oblique rotation, which is faster than direct Oblimin, and is sometimes used in very large data sets. Just if you're at all interested, everybody, I actually have I co-authored a paper with RAND Institute on evidence-based complementary, a survey that they created, and it is on the web that we published in 2010. The paper, you'll find it on the web as well as the actual paper. And we used a Promax rotation for this paper. And I do go into depth what Promax is. It's applied to the loadings. What it does is it actually puts a power, a k times the power, and it can actually weight the loadings. So the default for SPSS is k equals 4. What does that mean? Loadings for an item that are 0.6 and 0.3 are raised to a power of 0.4. So if you took 0.6 and raised to a power of 0.4, it's 0.1296. If you put 0.3 to the power of 4, it's 0.08, which means that ratio becomes 16.2 to 1. So the power of 4 is kind of an oblique rotation, but it does a better job of separating the items. A better job of separating the items. A value of 4 is generally recommended as an acceptable starting value. Here's one of the old classic books on exploratory factor analysis by Gorsuch, 1983. So you can also do a Promax, everybody, as a type of non-orthogonal. And the rotation is Promax. And as you know with oblique rotation, as you now know, you get a rotation sum of squared loadings, but you don't get percent of variance because they're correlated. And you get a pattern matrix and a structure matrix. Again, everybody, pattern matrix and structure, look at both of them. I know in some books they'll say interpret the pattern matrix, but use both of them. Use both of them. And hopefully they'll be similar. How can I tell that Promax is a type of oblique rotation? It gives me a component correlation matrix. It gives me a component correlation matrix. So here's just a little table I create in Excel, just to show you the different types of all the rotations we've gone through. It's kind of nice, everybody?
Yeah.
Varimax, Quartomax, Equimax, oblique pattern matrix, oblique structure, Promax pattern, Promax structure. So this just kind of shows you the factor loadings just for the first component. Just for the first component to see if they're radically different. They're really not. You don't see huge differences. I do see item 7 is a little screwy. Negative, 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 and I see it's slightly positive for oblique structure. And item 7 we know has been a little bit screwy. But for the most part, they're fairly similar. Item 8, which was a little unstable, I noticed is a little bit different. So here you get an idea that there's many differences between all these different types of rotations.
When you would look at these different kinds of techniques, would an item that is less stable maybe be an item that's not as good?
You know what? Absolutely. I'm not going to make that claim definitively, but it may be an item that merits further examination, that's not stable against different types of rotations. If I get an item that across the board, 0.85, 0.87, 0.86, 0.8, 0.83, 0.84, it's pretty stable. If I have an item that has a low communality, and given the types of rotations, the way that they render a solution, that might be a candidate for what's going on with that item. Which may mean that it's round 2 if it's a crucial enough item and you look back at it and say, oh man, we just didn't word it very well. We really didn't word that item. Then you may have to do a second version, possibly, and validate it on another sample. So it ain't easy to do this time. Now you know the different types of rotations. There's also different extractions. Thus far, we've been just using principal components. As the extraction, so rotate means how to help to interpret the solution. Extraction is what's going to help us extract the factors. And there's all these different statistical tools for extractions. many, many options for extraction. We've already gone over principal components, which is used to maximize variance. So it uses all the variance, everybody. What does h square mean? Communality.
It's the,
Communality.
yeah.
And u square is uniqueness. And it adds up to 1.0. So this is what principal components analyzes. It analyzes all the variance. Look at the ones on the diagonal. This is orthogonal rotation. The factors, of course, will have a 0. So it analyzes all the variance. It doesn't just make a distinction between common factor variance and the uniqueness. And as you know, uniqueness can be further partitioned into specific and met and error. So principal components, everybody, is the variable, the item, so to speak. Right, here you see where y equals principal component, where y is a component as a function of the items and a factor loading. In other words, x1, x2, x3. Here, do you see my arrows go this way towards the component? So here, the component is a function of the items. It's a linear combination. I feel sad today. I feel hopeless today. I feel down in the dumps. Principal axis factoring is this, that the items are a function of the construct. So you're going to find principal axis factoring is much more reflective of a structure equation modeling. In other words, soon you're going to find this would be called a model with formative indicators. The indicators influence this composite, this construct. Whereas here, the construct, this thing called commitment, depression, influences, so to speak, my response to the indicators. This one is much more reflective of what we call reflective indicators. Formative indicators, reflective. So this kind of goes visually with principal components extraction, and soon you're going to see that this corresponds more to principal axis factoring, or sometimes what's called factor analysis. See, look here, everybody. Here, the factor is a function of the items. Here, the item is a function of the components. So that's a very different rationale for which type of extraction you will use. So a lot of people, because the defaults of computers, will use principal components with Varimax. Whenever I get an article submitted, I always say, good, give me your justification. Why are you using the default? Tell me why. You gotta justify it, everybody. See, this one would be more aligned with principal axis factoring, which is aligned with confirmatory factor analysis. Because here, the items are a function of self-esteem, this thing called self-esteem. I don't feel so good about myself. I tend to beat myself up. I don't have much hope in my life. Depression, I feel hopeless. Impulsivity, I usually pick the first thing I can, etc. So here you see the items are a function of the construct, that thing inside of you, a latent, unknown construct. Your book that you're using is Psychometrics, and I don't know to what extent you're using it. It's not an easy book you have, by Rakoff and Markulides. I know Markulides, and I've reviewed articles by Rakoff. It's not an easy book, and I did tell Don, I go, be careful. One thing about that book, it's all based on a latent variable modeling. Even the chapters on reliability. I don't know how much you guys have read that book. Have you?
Yeah, I have several chapters.
It's not easy. It's
No.
based very much on a latent variable approach.
Yeah.
Which
Pretty
is not
technical.
which is not easy, and it's technical in a different way than most psychometric books. It's technical because, and that's because Rakoff and Markulides are very steeped in latent variable modeling, and probably if they have a chapter on factor analysis in it, I bet you they make the distinction of reflective and formative indicators. I bet they do, to show the differences of PCA and PAF. Principal axis factoring proceeds much the same as principal components, except the diagonals are communalities. In other words, it only analyzes the shared variance the factors have together. Principal components analyzes it all. Good stuff and bad stuff. This one excludes error and unique variance, because it's based on the belief that such variances only confuses the picture of underlying processes. Shared variance is determined by communalities or squared multiple correlation. Communalities are adjusted by what's called an iterative procedure. A lot of these statistical methods, everybody, from here on in, such as factor analysis, discriminant function analysis at times, structure equation modeling, multi-level modeling, logistic regression, they do what's called iteratives. They use these types of mathematical solutions, or what's called analytical solutions. Because you get an initial solution that might be based on the actual correlation matrix, the covariance, and goes through a round to optimize the solution. Then it goes through another round, and then another round, until it hits what's called convergence. How do you know when you got convergence? The default, a lot of times, is p-values of 0.001, or a change in the parameter that's not less than 0.01. In other words, what it might do is, okay, iteration 1 equals 4. Iteration 2 equals 3. Iteration 3 equals 2.999. Not much of a change there, is there? So it'll stop at the third iteration. So that's why you're going to see in almost all these statistical outputs, you'll see a little line underneath the table that says converged in so many iterations. It converged in so many iterations. If it doesn't converge, you got problems. If you don't get a solution, you got problems. So, what you're going to find, everybody, rotation converged in 8 iterations. There you go. The default is 25 in SPSS. The default is 25. If you look at even just do point and clicking, analyze, dimension reduction, factor, rotation. Let's see if it's under options. I never know under which. Here it is. 25.
So is there...
So if you don't get a solution, and I've done this, probably on 4 projects in my life. Sometimes I don't get a solution, and I just type in 50. I type in 50 and see if I get a solution at number 27. If it's taking much more than 25, at least for factor analysis, something screwy is going on. Flawed items, constructs are not clear. Small sample size, a lot of things can lead to lack of convergence. Some models are more complex that need more. It's not unusual in multi-level modeling to have 100 iterations. But with factor analysis, if you have 9 items, 200 people, it should go lickety-split. You should not have to need more than 25 iterations. Chad?
I'm just wondering, do you start to get worried when you get into
Yes.
some of those higher iterations?
If it's stopping at 25, and then I type in 50, and it does okay at the 37th, I'm going to look at the solution and see what's going on. Absolutely. Absolutely. So it means there may be, in fact, in the old days, you guys, variables, when they used to do journal articles on factor analysis, they'd have, eigenvalues, this and that, and they would have 2 columns. One column would be number of iterations and what's called computer intensive time. How much time it took the computer. Because in the old days, pre-PC, these things chugged along. Now, sometimes they even used to actually quantify how much time it took to render a solution. Now that is less of a problem. Well, I've had some multi-level models where I've had to go out to lunch and come back in about an hour and 40 minutes until the model was fine. I've had to do that with a client. One large client that got published that I didn't co-author, Risk Perception. That is a real known expert in crises. And he did a thing on bioterrorism and then the economy. And these models took about an hour and 40 minutes, about 100 minutes to converge. And he told me I could bill for it. I'm just sitting there on my computer because I couldn't work on anything else. And he said, Dale, go ahead and build. These are complex models. Okay.
But he wouldn't give you co-authorship?
On that one, though, I would have loved that one. He didn't need to. He paid well. I would have loved that. It was a big article. It's by Slovak, who's one of the big people in decision making. It's co-authored with Slovak. There were some big hitters on this one. So that being said, everybody, let's go back down to principle. So principal access factoring puts commonalities on the diagonal, which means it gets rid of unique variance. So if you want empirical summary, then use principal components. But what do I mean by empirical? This is see what the results are. Let's go ahead and put it in the machine and maximize variance. But a PAF is more akin to a latent variable model, and I'm sure you'll go over that in your psychometrics class. If you want a theoretical solution uncontaminated by uniqueness, use FA or PAF, which is factor analysis. Now, one thing you're going to find, everybody, when you use principal access factoring, PAF communalities are going to be smaller. Your variance explained is going to be smaller. Across the board, it's going to be smaller. Because we're excluding error variance, right? It's got less variance to partition and to explain. Look, everybody, now look at number 9 item. It's all the way down to 15%, 22%. So you do start seeing lower loadings. And look at the initial, everybody. See, it's no longer 1.0, because remember, principal components analyzed all the variance. Remember, put a 1.0, because it analyzed all the variance. Here, it only looks at the shared variance. So you remember communality? Put 1.0 in the diagonals, because it analyzed all the variance. Look at this, everybody. 48.8 for item 8 for principal components. Now it's 37.1. So you do get differences. And you get this thing called a factor matrix. You really don't have to interpret it. Similar to the component matrix, the principal components, you'll tend to have a G factor. You'll tend to have one big factor, but this is crucial for getting at a solution. But guess what, everybody? Look what we got. More than 25 iterations required, extraction was terminated. Do not ignore that message. Do not pretend it doesn't exist. Because you won't get a solution in SPSS. Other software may still give you a solution. But it means that, you know what? You see the convergence of 0.03? Unfortunately, it did not get reduced beyond that. Which means, here's your factor matrix, everybody. And we did not get a solution. We didn't get a solution. So look what I'm going to type in. I think I'll just type in 100. And I'm going to confine it to 2 factors. And look what happens if I get, or let's see if I get rid of, I'm sorry, let's not keep 2 factors, but let's get rid of item 9. Because item 9 had 15% explained. Now I get a solution. Do you see what happens if I got rid of item 9? 50% is explained. I get 3 eigenvalues greater than 1.0. So that's sometimes some of the things you may need to do. But let's play around, everybody. Let's play around here just to show you this. Just to show you what happens to the machine. Analyze, dimension reduction factor. Let's put in the first 9 items. And under extraction, let's do principal access factoring. Rotation, we'll use Verimax for now. There's my little error message. More than 25 factors, iterations, extraction was terminated. Now I still got a solution. It still spit out a solution, but I would be cautious about it. It still spit out a solution. So let's see what happens. Zach, being the kind of guy he is, says, I know how he can work around this. I'll just type in 100 rotations, 100 convergence, iterations. Didn't quite work. So I would be very cautious about this solution. But you saw that when I got rid of item 9, it worked. So for principal components, we got a solution. For principal access factoring, we didn't. So if I did 2-factor solution, or got 2 factors for 9 items, then it renders a solution. And item 7 had too low of a variance. So there's different ways you might have to start playing with your model, everybody. With your model. So here, everybody, I wanted to show you the comparisons for principal components and then principal access factoring, just the Verimax. The loadings will tend to be lower because you're only analyzing shared variance. They'll tend to be lower. Look at this, everybody. Principal was 0.054 compared to negative 0.175. So there are some differences in different rotations and different extractions. And 49% is explained instead of 65. which is real typical. So that, everybody, those are mainly the main rotations and extractions you'll use for this class. Minimally, what I do for my clients, just to see if they're similar, I'll usually do a Varimax for my orthogonal, and I'll do a direct oblique for my orthogonal. So Varimax for orthogonal, one for the oblique, direct oblique for the oblique, so 2 types of rotations. And minimally, I'll do 2 types of extractions. Principal components, which analyzes all the variants, and I'll also do principal axis factoring. And then there's other ones that probably are used much less frequently. Unweighted least squares. It's a factor pattern matrix that minimizes the sum of the square difference between the observed and the reproduced correlation matrices. You already saw that. You have your actual correlation matrix, a reproduced one, and then the difference is the residual. So basically, it ignores the diagonal, the variances. Only off diagonals are considered. So unweighted least squares is one option, everybody. What's called unweighted least squares. I don't use it often. I've used it a couple times in structure equation modeling. I've used it a couple times. It's fast. It's very fast. And then you can see if the solution is radically different. Lots of papers, you guys, lots of papers out there in factor analysis. Nice user-friendly articles, such as best practices in EFA, 4 recommendations for getting the most from your analysis. Really nice user-friendly papers out there because it can be overwhelming to really learn it. This book only touches the surface. Usually there's entire chapters, just one on principal components, one on principal axis factoring. Lots of decisions that go into doing a good EFA. Another one, which one of your colleagues, one of your students is proposing for a dissertation, which I don't feel she has enough justification yet, so I think she needs to understand, is maximum likelihood. This produces estimates that are most likely to produce the observed correlation matrix. In other words, maximum likelihood, which is the black box for logistic regression, it's the black box for structure equation modeling, it's the black box for multi-level modeling, is it basically produces parameter estimates, which could be means, covariances, odds ratios, and it produces them initially, and those that are most likely to lead to the actual correlation matrix, the actual mean. The one way to look at maximum likelihood, everybody, one simple way, is let's say you know that the population mean for depression is 25. Okay, you got all these parameter estimates that can go from 0 to 50. So if I plug in a 5, is that very close to 25? A 6? A 48? A 27? Is that closer? So which means I can literally, via numerical integration, good old calculus, get at the probability of each of these, multiply the probabilities, and try to get parameter estimates that will maximize the likelihood of that sucker. So guess what? You need computers. Maximum likelihood, I'm sure someone did it by hand pre-70s. It actually started with the Education Testing Service, SATs, et cetera, back in the early 70s, when statisticians and methodologists were playing around with these iterative types of solutions. So here, maximum likelihood, correlations are weighted by the inverse of the uniqueness. So it's kind of like weighted, remember weighted least squares from regression? When you can weight the residuals? Those with bigger residuals got less weight. And it tries to get at estimates for factor loadings. Clean this up a little here. Population estimates for factor loadings are calculated that have the greatest probability of yielding a sample with the observed correlation matrix. And this is the black box behind many, many, many multivariate stats. So here you get maximum likelihood, 52%. So it's lower than PCA. You get a rotated matrix, probably pretty similar, but look what you get. The goodness of fit test. So now you actually get a chi-square test of the goodness of fit, which generally you don't want significance. Usually for the goodness of fit, you don't want significance, because you want the model to fit the data. So degrees of freedom are a function of number of common factors and number of variables. We have 3 common factors, 9 variables. What's 3 plus 9? 12. And And here we get, I kind of did a lot of the mathematics here to convert the chi-square, but essentially, do you see the P of 0.042? It's significant. So the model doesn't fit very well, everybody, and we already kind of know that. We know it's not perfect. So one cool thing about maximum likelihood is I can compare nested models. What if all of a sudden Chad says, well, Dale, that 3-factor solution isn't working out so well. I'm going to constrain it to 2. I'm going to constrain it to 2. As you would guess, the fit would get worse. Right? It's already bad with an unrestricted model. Now we have what's called a restricted or constrained model. And what you can do is, you see the p-value? It got worse, actually. It's a higher chi-square, which you would expect a higher chi-square. And what you're going to find, especially if you ever get knee-deep into structure equation modeling and start to compare multiple models, if you use what's called maximum likelihood, which assumes multivariate normality, you can actually subtract 44 minus 21, divided. 44 minus 21 is 21. What's 19 minus 12? 7 degrees of freedom. Go to a chi-square table. Go to your good old chi-square. Look for the critical value of 7 degrees of freedom and see if they're significantly different. So you can actually test via maximum likelihood if there's significant differences. And that's pretty cool. And if you like, you can take differences in chi-square which would be, as you know, 44.43 minus 21.611, and use critical value for chi-square table based on difference in df, which is 19 minus 12, which equals 7. And if it's significant, if it's exceeded, it means one model fits better than the other. Usually the more restricted model, which means the easier model. So that's maximum likelihood, everybody. Very similar as generalized least squares. This also gives you a goodness of fit test and minimizes the sum of the square differences between the observed and the reproduced correlation matrices, minimizes the sum, and it's the same, so which means it's the same as weighted least squares. But correlations are weighed by the uniqueness, which is the residuals. You have the actual correlation matrix, the reproduced, and the difference is the residual. So it weights the residuals. A lot of times, generalized least squares may use a variance-covariance matrix as a weight. So a lot of these statistics, everybody, use a weight. Correlations involving variables with high uniqueness are given less weight than low uniqueness. And we're happy there. The P is 0.10. However, you got to make sure you have multivariate normality. It really wants multivariate normality. And there's the rotated matrix. Then there's others. If those are not often used, everybody, this is even less. I rarely see image factoring. It's a linear regression on the remaining variables rather than a function of hypothetical factors. So you have a residual about the regression, which is the unique part, and then it does a regression on that. So it's kind of like square multiple regression holding other variables constant. I rarely see image factoring being used. It's kind of arcane. I've just never seen many people use it. But you can play around if you want to. You have a slow Saturday night, and you say, wow, I think I'll try image factoring. And look at the percent of variance, though, everybody. It really goes down all the way to 34%. And I'm going to skip through this. Then there's even an alpha method. This one I've rarely seen. This actually uses the reliabilities. It actually considers the variables analysis to be a sample from a universe of variables. It maximizes the alpha reliability of the factors. So with alpha factor extraction, eigenvalues are no longer obtained as sum of squared factor loadings, as the communalities are not the sum. So this actually gets, as you maybe learned when you got a reliability, you probably talked about the universe of items, or what's called domain sampling. Let's say for organizational commitment, there's a universe potentially of 65 items. Do you think you're going to use 65 items to tap OC? You're going to use a pool of the universe of items, and that's called domain sampling. So this kind of reflects that notion of sampling from a domain. And you can see 48%, very similar result. So I did all these in the notes, everybody, just to show you all the extractions in SPSS. I just went through every single extraction, and there are more out there. There's other programs with more extractions. You will not have to worry about it. But I want to show you that there's all different ways to think about extracting your solution. The two main ones you'll use are principal components and principal access factor. Those are the main ones we'll use for this class. And for just for funsies, here's the comparison of all the extractions. Just again for the first factor. So here I did all the PC, PF, unweighted least squares, and maximum likelihood, just to see if there's much of a difference. I notice image seems to be the one that really seems to divert quite a bit. So here you actually have a comparison. And you guys, if you do a couple of rotations, a couple of extractions, they all show similar results, you're fine for that sample at hand. So in my own work, everybody, I tend to run at least 4 EFAs. Orthogonal with PC, oblique with PC. Orthogonal PF, oblique. And if I find a solution similar, great. If not, then as Zach alluded to earlier, and maybe I can start seeing what maybe other particular items that are more problematic. Another goal that I usually don't use it for, bless you, is to construct what's called factor scores. You can reduce the large number of variables to a small number of factors, and for each case, they get a factor score. So if I get a 3-factor solution, each individual gets a factor score. And those can be used as predictors. They can be used for analysis. So, as long as communalities are estimated, factor scores suffer from what's called factor indeterminacy. Which means, you know what? There could be an infinite number of possible factor scores given the solution. It is possible, as even with structured equation modeling, I can get different types of results that fit different types of plausible hypothetical relationships. That is not at all implausible. But factor scores, you can save factor scores right there. And you can save it if you want. And there's different types of method. The regression, Anderson-Rubin, there's different types of factor scores. And you get a brand new matrix that you will never have to use, but it's called a component score coefficient matrix. This matrix helps the mathematics to get a factor score for each individual. Component score coefficient matrix, it's a function of the factor component score, which equals the inverse of the correlation matrix times the factor loading matrix. So you see, it's all deep matrix algebra. This is all matrix algebra. So factor scores multiply the standardized values by the factor score coefficients. And how can I tell I have an orthogonal rotation here? Look at the correlation of the components. What do you notice the correlation of the components is? Yes. So there, that makes sense that for the factor scores, they're going to have 0 correlation. What you do get then, everybody, in your database, you get 3 columns of brand new data. They're called factor scores. They're based, so in other words, this individual, for the first construct, these are basically a derivation of the squared loadings, so to speak, or the loadings for that first component for all items. Why do I say all items? Because this is called an unrestricted model. All 9 items load on all 3 constructs. They just have different loadings. So there, you can maybe use these as variables if you want to in a regression. No surprise. Guess what? They're types of z-scores. They're essentially, how can I tell these are type of z-scores? Mean of 0, standard deviation. There you go, they're type of z-scores. Again, are you surprised that the correlations are 0? Nope. But look at oblique. Do you see that, everybody, from the oblique matrix? And surprise, surprise, exactly the same when I create factor scores. Exactly the same as that last little table you get for oblique rotation. So here, everybody, this takes into account the intercorrelation of the constructs, which is pretty realistic in IO psychology. Now, a point on extraction. Some have doubts about the scree plot. Some have doubts about the Kaiser criterion. You're going to find articles, pro and con. I don't know if this is what you were referring to, Zach, but there is a macro you can get at to help determine the number of factors that goes beyond the solution in SPSS or SAS. It's called parallel analysis and minimum average partial test. The main article is an old article by Glaser in Multivariate Behavioral Research at Journal of Applied Psychology. And it's a wonderful way to be able to get at the number of factors. So the original MAP test is a 76 article by Glaser in Psychometrica. And then it was updated in 2000. And this O'Connor did a beautiful job of creating macros in SPSS and SAS for determining the number of components. It's in behavior research methods. And let me show you how you do this. You download the macro, and you can actually do this. Usually you have to use an include statement, or you can invoke it within the file. So here's two ways of running the program. You can enter a correlation matrix directly into the program without having SPSS save it, or you can use the command compute to get at this. Or you can have the program read a correlation matrix that was saved by SPSS. How do you save a correlation matrix in SPSS? Here's my 9 items, right? Do you see correlation, the items? Matrix out. I don't know if any of you have ever used that option, but it provides a matrix. I'm going to call it multi-class core. And then I can do factor analysis, variable, and matrix out, multi-class core. So these create the matrix variable. When all said and done, everybody, then you use this MGET syntax. There's my correlation, multi-class core, and here's the minimum average partial test by Glaser. So it's really easy to use. And look, the eigenvalues are exactly the same from the principal components. 3.73, 1.14. And then it gives you these average partial correlations. These average partial correlations. And we see the smallest squared one is 0.0428. And the smallest there we see is 0.038, which tells me the number of components according to the original MAP test is 1. The number of components is 1. Guess what it's telling me, everybody? Maybe there's only one suitable factor here. The second one did okay. The third one was screwy as hell, right? So this one can help you for getting an understanding of how many components to retain. Also is the parallel analysis program. And I'm not sure if this is what you were talking about, the Monte Carlo option, but it does do compute number of data sets, for instance, 1,000. And it generates all these eigenvalues based on the number of cases. We have 146 people, 9 variables. You might want to play around with the seed number, which helps with the random number generator. Compute 95%. Look, you can desire, specifies the kind of parallel analysis, principal components, principal axes. Parallel analysis, if actual eigenvalue is greater than random eigenvalue, make a retain decision. If it's less than, then it's noise. So here, everybody, all of our 3 actual eigenvalues, right, which we already know, are random or greater than random, so okay. In other words, all 3 of our actual eigenvalues, when we look at the eigenvalues, were greater. Here again, you can see 3.7, 1.14, 1.02, and you can actually use that to compare or grade the eigenvalue, looking at the means. So you can use this to maybe get an idea of component retention. I would read the initial articles But those are great things to start supplementing how many factors to potentially retain. And I don't know if that's what you were alluding to, that uses a computer sampling method. But I have a feeling that's what you were thinking of.
The video I saw online, it actually imposed a line on the screen plot that sort of matched up, so you could tell. I don't know.
Oh, okay, so it's not probably this.
I don't think it was. I don't think he used a macro. I forget exactly. It was a couple months ago. But.
Okay, everybody, so that's the brief lecture on EFA. It can be a lot more complex, but you kind of get an idea. And it's a tool I use whenever I have a client use instrument development. Now, I do want to say, if my client comes and they're pretty certain which items load on which constructs, I'm going to go straight to CFA, which we're going to talk about towards the end of the semester. I'm going to go straight to confirmatory as opposed to exploratory. So your next homework, you're going to do EFA for all 23 items in the homework database. So looking at your homework, everybody. You've got 23 items. Do not use the overall item. Now, what's going to give it away is we kind of already have names for each of these. So usually I kind of do a name the factor. Right? That's part of the fun time, is naming the factor, making sense. So get creative. If it doesn't come out to this, create your own name if you can. I want you to use at least 2 types of rotation. Varimax and Oblique is absolutely fine. 2 types of extraction, PC and PAF. See if you get similar results. I don't need you to report every single one multiple times. That'll be a 20-page homework. You can start with 1, then use that as a basis, and then if you even want to do a little Excel table just to compare a little bit, I'm fine with that. And interpret the results. I know we have a name of the construct in the database, but it'd be nice for you to create your own label, especially everything may not work perfectly. Right? Everything may not work perfectly the way you think. So that, everybody is your homework.
Next week.
It's due next week. So, let me see something here. Any questions on EFA? Again, a lot of the chapters on CFA, which we're going to get knee-deep into later on, towards the end. Let's start on canonical correlation. A little bit of time. Or let me see something really quick. Let me see if I have this one thing. Hold on for a second, you guys. No, I don't have this with me right now. I actually had this one instrument that I had from Kouzes and Posner, which is a leadership scale. And I actually had this thing that I used to kind of do as a little in class to kind of name the construct. But I think it's changed so much, I don't have that. What I'd like to do very briefly, start on canonical correlation. So one thing I want to say before we start is use EFA prudently. I see a lot of people go straight to the defaults of Verimax and to principal components, and that may be fine, but then you need to justify it. So what's the point? The days of just using the defaults without saying, why are you using that type of rotation? Why are you using that type of extraction are kind of gone. But EFA, you guys, you've got a dissertation. As you know, it'll be 2 dissertations in one if you also create an instrument. You have a 30-item instrument that's going to get an employee engagement. You have no idea how, your thinking hasn't crystallized enough to do this, but you probably have an idea. I'd be really shocked if any of you ever create an instrument and you don't have an idea that maybe 4 items get an engagement, 3 in commitment, but you're at that point of uncertainty. You're at that point where I'm going to do EFA. Then I'm fine. But if you're at this point, everybody, if you're pretty solid that these items measure this, these measures go straight to CFA. There's no reason to do EFA. The bad news is if in your dissertation you want to do EFA and CFA on the same instrument, Guess what I'm going to require you to do? To do it on 2 separate samples. You don't get to use your 700 people that you fought tooth and nail for and do the EFA, and then on the same sample do a CFA and find, wow, what a great solution, everything works out well. Well, yes, because you used a solution for your initial sample. So the bad news is, generally it's recommended you do an EFA on one sample and CFA on another. Now, sometimes people do what's called holdout samples. If you have the luxury of a large sample size, which I did for an AP presentation, I had the luxury of 7,000 people for an optimism scale. So I did 3,500 EFA, 3,500 CFA. It came under no criticism whatsoever at APA. If I was critiquing my work now, I would criticize it.
Why?
Because they still came from the same sample, all 7,000. It wasn't like I did one at California, one in Rhode Island. I did them all from the same sample, same set of recruits from the Navy. So that's a potential argument. But that's what a lot of people used to do, Zach. They just hold out samples, randomly split the file, and do EFA one, CFA the other. If they should converge, you shouldn't be shocked because it's from the same sample. That would be the hardcore critique.
But I mean, if you're just interested in military, then
Yes,
wouldn't that be
then
okay?
if you could make that argument. If you could make that argument, yes. Right, exactly. Okay, everybody, briefly, I'll spend a little intro and let you out. Da-da-da. Has anyone in this class, before this class, can I assume you all have heard about factor analysis, or heard about it or read about it in articles? You knew what it was a little bit? Has anyone ever heard of canonical correlation? Has anyone in this class? In what context have you heard about canonical correlation?
Reading for this class.
What is that?
Reading for this class. And in some of the videos that I've watched, it's been mentioned. And I just remember because it's novel to me because I didn't know much about it.
It's also novel because some people think it's obsolete. There's some people that feel, almost all multivariate books shouldn't even have chapters on canonical. You're not going to have to run one of these, I don't believe. But it's good to know about it, because I actually had the opportunity to co-author a paper 3 years ago using canonical. And it was perfectly logical sense. Because what if you have 2 sets of variables? What if you have 2 sets of variables? One are a bunch of organizational attitude variables, job sat, job stress. Another set is a bunch of demographics, number of years on the job, salary. What else could be a continuous variable that kind of gets that demographic for organizations?
Tenure.
What's that?
Tenure.
Tenure. What else? Tenure, salary, age. What else? What else might be a continuous variable? That's kind of a demographic. Can you think of any others? Education, number of years of education, right? So what if you wanted to reduce the dimensionality of these two? What if you have all these job attitude variables, all these demographics, and you wanted to see if they form, hopefully, an interpretive and coherent number of dimensions? Are you getting an idea, you guys, that this whole class deals with linear combination of variables? Do you see it's constantly down to that? But now, similar to EFA, we want to reduce the dimensionality. So I'm going to start off really easy, almost too simplistically, but this will show you how it works. This is from the Sesame Street database, which comes from your book. Now, I'm beyond the generation that ever watched Sesame Street. Maybe I watched it once with my stepkids a long time ago. Did any of you ever watch it as kids?
Oh, yeah.
Did we like Big Bird and everything?
Grover.
Grover.
I'm a Grover fan, yeah.
Okay. Did you learn much about letters from the show, Zach?
Oh, yeah.
Did you learn much about forms, like circles versus squares versus triangles?
Mm-hmm.
Okay. Could I do a pretest on Zach and his ilk on his knowledge of forms and letters, have him watch maybe some Sesame Street, then do a post-test?
Yeah.
Good. So maybe there's 2 sets of data I have here. Pre-tests and post-tests. Okay, let's just say for now. Pre-test, post-test. This is the simplest example of it, but I just want to show you that you can take 2 types of data sets. And essentially what you're trying to do is decrease the dimensionality of the data. So what if I had 10 organization attitude variables, 10 demos? Do you think I've got 20 different constructs there? What if you found with organization stress, what demos might go together with that? With organization stress, organization anxiety, and organization worry. I'm going to make those three up. What might go with those? What demos?
Position?
Maybe position. That's a categorical variable which adds complexities, but
Salary,
maybe salary. Can you think of a second demo that goes?
tenure.
Maybe tenure. There's a dimension, so to speak, that might logically go together. So, it's kind of like multivariate regression. Remember multivariate regression? You had multiple outcomes and multiple predictors. But multivariate regression did not reduce the dimensionality. It just gave you the regression weights for each outcome and a multivariate test. Here we're trying to reduce the dimensionality. So, how do you do canonical correlation? There is no point and click for an SPSS. There's no canonical correlation. There is a macro. There is a macro, though, that you can download that I have also included. That I've saved you the trouble of having to download. But I have included the macro. But if you wanted to download it, if you really wanted to see where the macro is, if you do File, Open, Syntax, go to your C drive, go to Program Files, go to IBM, go to SPSS. No, I don't want Amos. Or maybe it's a different IBM. It should be SPSS, Amos. There we go, 19. And then go to, where would they put it? Examples, English. This isn't, oh, okay, hang on you guys, this has really changed.
Bush.
Oh, bless you. Open, syntax. Let's go back to maybe I won't be able to access it from here. Let's try it one more time. Let's just do program files, IBM, SPSS, statistics, 19, samples, English. So, you guys don't have to do anything with this. It's someone spent the time doing this. You ask me what some people may do in biostats, they won't necessarily do this, but they'll do a lot of programming. Like the masters, not this extent, but they may create macros. I know statisticians do that. So here, you guys, here's the macro. You don't really have to look at it, but you can save it in a file, and as you did with the multivariate normality, you're going to invoke it. Include file and 2 lines of code. Canonical core, here's your first set, your pretest. There's your second set, 2. That's all you have to do. That's all. That's all you need to do. You invoke the macro, put it in a subdirectory, and there's how you can get at canonical correlation. So why don't we stop here, and I'm going to go through the output. Canonical correlation, in the old days there was an article called The Most General Linear Model. So for a while they thought regression was kind of a general linear model. Then there was an article years later about canonical correlation being the most general linear model. Then there was another article that superseded called structure equation modeling is the most general linear model. So here you really have 2 sets of multiple outcomes and multiple predictors. And they're 2 sets. And this is really a true multivariate type of modeling. It's not used very much. It really isn't used that often. Some people think it's obsolete, but I found this worked perfectly. Let me see if I can find it really quick, guys, before you go. Let me see if I can find it. Here's an article. Let me see. And you know what? It was for this study, but we did it for a study part 2. We looked at barriers among healthcare. We did barriers among healthcare and evidence-based practice. and we used a canonical correlation. We used canonical correlation with all these variables that did barriers to healthcare and evidence-based practice and certain attitudes towards evidence-based, and we found a more parsimonious combination. So for this article on multi-institutional study of barriers to research utilizations and evidence-based practice, we actually were able to use canonical correlation for this. That's the only time, you guys. The only other time I've used it is for a dissertation from someone from Fordham University. They did a bunch of multivariate stuff for their dissertation. I mean, they did MANOVAs, multi-level modeling, they were doing all types. And one of the things was doing a canonical. So if you ever someday get a project with two logical sets of variables, and similar to exploratory factor analysis, you want to reduce the dimensionality of it, canonical correlation is definitely one option you want to investigate. And we'll get into the actual output very briefly next week. So you guys are free to go. Take care, be good, and we'll see you next week.